Let's take a look at some special applications of circular motion. We'll start with a conical pendulum. In a conical pendulum, our mass is on a string and it's swinging in a horizontal circle like this. My image on the screen captures the object at one instant in time, but it's actually swinging around in this horizontal circle. So draw a free body diagram, and in your first free body diagram, just draw the forces as they actually appear. Then pick an appropriate coordinate system and break the vectors up into components in that coordinate system. Here's my free body diagram. Now I have to pick an appropriate coordinate system. Well, I could pick the direction of my string, the direction of my tension, and perpendicular to that. But what question do I always ask myself when I'm picking a coordinate system? What direction is the acceleration? And this is an object moving in a circular path. What circular path? This horizontal circle. So the acceleration has to be toward the center of the circular path. The acceleration has to be in this direction. So I want my coordinate system to have a component in this direction and then perpendicular to that. So I'll pick this as my coordinate system, and I'll redraw my free body diagram, splitting the vectors into components that are in this coordinate system. That means I'm going to have a t cosine theta in the vertical direction, t sine theta in the horizontal direction, and the force of gravity doesn't change. It just points towards the center of the Earth, which is aligned with my coordinate system. How did I get cosine theta and sine theta? Well, the angle was given here as theta, which means that this angle here would also be theta. So the adjacent side would be t cosine theta, and the opposite side would be t sine theta. The hypotenuse is t, the tension in the rope. When you break up vectors into components, the components should always form a 90-degree angle. That means that the vector you're breaking up is always the hypotenuse. That might help you as you break up forces into their components. So in this problem, if we were given the length of the string in theta, and we were being asked to find the speed of our object as it goes around, then we would treat this as a forces problem. Sum of the forces equals ma. That's what we do with circular motion problems, because we know the acceleration in the radial direction has to have this special value, v squared over r. So let's do that. And I'm going to add them all up. I'm going to pick toward the center of my circle as the positive direction, radially inward. And that means I only have one force in that direction. That's the component of the tension toward the center of the circle, t sine theta. And that has to be mv squared over r. And what r are we talking about? Let's look at our picture. R is the radius of the circular path. So in this case, the mass is moving in a horizontal circle. R is the radius of that circle that it's moving in this circle. So it would be L sine theta. Now we know one more thing about this. We know that the mass is not going up or down. It's always staying at the same height as it goes around that horizontal circle. So the sum of the forces in my perpendicular direction have to be 0. There's no acceleration in that direction. So that tells me that t cosine theta equals mg. So from this and the other equation, I can combine those two equations and I get the tangent of theta is v squared over gr. And r is L sine theta. And if I was given L and theta, I could get v from there.